Every world has its own Everest. The highest summits in our solar system are nothing like you imagine. Some are forged by cataclysmic impacts that punch a planet so hard they wrinkle the crust on the far side, and others are capped with heavy metal frost or supported by hidden oceans. Measuring a mountain here isn't as simple as it sounds, and the true giants break every earthly rule. So what makes a mountain the tallest, and why do the biggest peaks appear on the smallest worlds? Measuring the height of a mountain sounds simple until you leave Earth. Here we are used to counting from sea level, but most worlds have no oceans and no easy starting point. So what counts as the tallest mountain in the solar system depends on how you draw the lines. Some scientists measure from a planet's average surface called the datum. Others look at the true base to peak relief, the vertical distance from the lowest visible base to the highest summit. Both methods have their champions, and both can crown different winners. Take Olympus Mons on Mars and Rhea Silvia Central Peak on Vesta. Olympus Mons is the classic giant, rising 21.9 kilometers above the Martian plains, more than twice the height of Mount Everest above sea level. But if you measure from base to peak, Rhea Silvia on Vesta, a battered asteroid barely 500 kilometers wide, stands even taller. Its central mountain, born from a cataclysmic impact, shoots up 22.5 kilometers from the crater floor. That is the tallest measured climb anywhere in the solar system by this yardstick. Every world presents its own measurement headache. On Earth, the ocean supports mountains like Mauna Kea, letting them rise higher from base to peak than Everest, even though Everest's summit is farther above sea level. On Mars, the crust bulges under the weight of Olympus Mons, warping the local reference surface so much that the summit's true elevation drops by hundreds of meters, depending on where you measure from. On small bodies like Vesta, gravity is so weak that rock strength, not weight, limits how high a peak can stand. That is why a mountain there can reach nearly 50 times higher than the tallest structure on Mercury. So, as we set out to climb the solar system summits, keep these two rulers in mind: elevation above the local reference and the raw distance from base to peak. Sometimes the winner depends on which one you use. If you are enjoying this deep dive into the heights of the solar system, please subscribe now. That is the only time I will ask. Now, let us get back to the climb. Mercury doesn't build mountains the way Earth does. Instead, its greatest peaks are the scars of a single ancient collision. About 3.5 billion years ago, an object the size of a large asteroid slammed into Mercury's northern hemisphere, carving out the Caloris Basin, one of the largest impact craters in the solar system. The energy released was so enormous that the shock waves didn't just ripple outward, they punched straight through Mercury's iron core and converged on the exact opposite side of the planet. On that far side, the crust couldn't take the strain. It buckled and shattered, leaving behind a jumbled landscape known as the Weird Terrain. Rising out of this chaos are the Caloris Montes, a ring of mountains that stretch up to 3 kilometers above the surrounding plains. These peaks aren't the result of slow uplift or volcanic eruption. They are the geological equivalent of a bruise, evidence of a planet-wide punch that deformed Mercury's surface in an instant. The process is as strange as it sounds. When the Caloris impactor struck, it sent a focused blast of energy through Mercury's dense interior. Instead of dissipating evenly, the shock waves met at the antipode, the point directly opposite the crater. The crust there was forced upward, crumpling and cracking into a maze of hills and ridges. Later, spacecraft like Mariner 10 and Messenger mapped this region in detail, confirming that the mountains and chaotic terrain match exactly where the shock waves would have converged. Mercury's highest mountains, then, aren't the product of tectonic plates or volcanic hotspots. They're a monument to violence, a reminder that on some worlds, the tallest peaks are made not by building up, but by being battered down. With only 3 kilometers of relief, Caloris Montes doesn't compete with the giants of Mars or Vesta. But its origin story is one of the most dramatic in the solar system. and it sets the stage for the strange and varied peaks that rise on every other world we'll visit. Venus is a world where the rules of geology are rewritten by pressure and heat. The highest mountain here, Maxwell Montes, rises 11 kilometers above the battered plains of Ishtar Terra, taller than any peak on Earth. But the real mystery waits at its summit, where temperatures hover around 470 degrees Celsius, and the air crushes with a force 90 times greater than sea level on Earth. When the Magellan spacecraft mapped Venus in the early 1990s, its radar painted a puzzling picture. Maxwell's upper slopes shone with a brightness that defied expectations. At first, scientists wondered if they were seeing echoes from water ice, just as radar bounces off the poles of Mercury. But on Venus, ice cannot exist. The heat here melts lead. The answer, it turned out, was even stranger. At the summit, the air is just thin and cool enough, by Venusian standards, for certain metals to condense out of the atmosphere. Deep below, compounds like lead sulfide and bismuth sulfide vaporize, rising invisibly through the thick carbon dioxide air. As they climb, the temperature drops ever so slightly. Near the peak, these heavy metals reach their dew point and settle as a thin, bright frost. It is not snow as we know it, but a metallic rime, coating the rocks in a layer of lead and bismuth crystals. For the Magellan science team, the discovery was a revelation. The summit's brightness matched exactly what you would expect from a coating of metal sulfides. On Venus, the highest mountains wear a crown of heavy metals, forged by chemistry and pressure rather than cold. The planet's crushing atmosphere does not just shape the land, it decides what can survive on the heights. On Maxwell Montes, even the snow is toxic, and the only thing that glitters is metal. Mauna Kea rises quietly from the Pacific, its snow-capped summit a familiar sight in Hawaii. But the true mountain, the part most people never see, begins far below the waves. From base to peak, Mauna Kea stands about 10.2 kilometers tall, making it the tallest structure on Earth when measured from its foundation on the ocean floor. Everest claims the highest point above sea level, but Mauna Kea is the heavyweight champion in sheer vertical relief. The secret lies in how Earth's crust behaves under pressure. Mountains built on continents like the Himalayas push down on thick, buoyant crust. As they grow, the crust beneath them sinks deeper, a process called isostatic adjustment. It is like adding weight to a floating raft. The raft sinks lower as you pile more on. This natural limit keeps continental peaks from climbing too high. Mauna Kea, though, is a shield volcano built on dense oceanic crust. Lava flows outward for miles, spreading the mountain's weight over a broad base. The Pacific Ocean acts as a cushion, supporting the mountain and preventing the kind of sinking that holds Everest in check. The ocean's buoyancy allows Mauna Kea to reach heights that would be impossible on dry land. Geophysicists at the USGS have mapped the mountain's submarine slopes in detail, using bathymetric surveys to trace its true profile. Their data confirm that more than half of Mauna Kea lies underwater, hidden from view. This submerged giant shows how water can shape the scale of a mountain, not just its surface. On worlds without oceans, like the Moon, mountains are preserved by vacuum and time. But here on Earth, the sea gives Mauna Kea its hidden height and quietly rewrites the record books. On the Moon, height is measured not by what rises, but by what endures. Mons Huygens stands 5.5 kilometers tall, a solitary rampart on the rim of the ancient Imbrium Basin. Unlike Mauna Kea, which owes its stature to the buoyant push of the Pacific, Huygens is a survivor. It is a wall of debris left behind when a cosmic impact reshaped half a hemisphere nearly 4 billion years ago. The Imbrium event was a collision of staggering violence. An object likely 250 kilometers across struck with enough force to melt rock and scatter ejecta across thousands of kilometers. The basin it gouged is more than 1,000 kilometers wide, but not all of the rim was erased. In places like where Huygens now stands, the crust buckled upward and froze in place. What began as a ragged ring of high ground has, over eons, been pared down by the constant bombardment of micrometeorites, but never erased. On Earth, wind, rain, and tectonics grind mountains down to stubs. On the Moon, there is only silence and the slow sandblasting of space. Without atmosphere or flowing water, even the tallest peaks can survive for billions of years. The Lunar Reconnaissance Orbiter and the Japanese Selene mission have mapped Mons Huygens with laser altimeters, tracing every battered slope and sharp ridge. The mountain's profile today is a testament to preservation by vacuum. Its summit has not changed shape since before complex life evolved on Earth. For lunar mappers, Huygens is more than a relic. It is a living record of the Moon's violent youth, a monument left untouched by the processes that reshape mountains on every world with air and water. Here, in the stillness, height becomes a measure of endurance. Olympus Mons rises so gently from the Martian plains that standing on its slopes, you might not even notice you are climbing the tallest volcano in the solar system. The base of this shield stretches across a landscape the size of Poland, sprawling more than 600 kilometers from edge to edge. Instead of a steep cone, Olympus Mons is a colossal dome with slopes barely tipping 2 to 5 degrees, so shallow that the horizon seems to fall away as you walk, rather than the ground rising beneath your feet. Planetary geologists first mapped these subtle inclines using the Mars Orbiter Laser Altimeter, revealing a mountain whose true scale is almost impossible to grasp from the ground. The summit stands so far above the surrounding plains that if you were to drive from the base to the top, the climb would take you through every layer of Mars's thin atmosphere, from dense dust storms to the edge of space. Yet the ascent is so gradual that a hiker could set out across the flanks and never see the summit looming above, only the world curving away in every direction. What makes Olympus Mons possible is Mars itself. The planet's gravity is just 38% of Earth's, so the rocks that make up this volcano weigh less and can stack higher without collapsing. On Earth, a mountain this size would sink under its own mass, the crust buckling and the peak slumping downward. Mars does not fight back as hard. Here, the crust is thick and immobile, with no shifting tectonic plates to drag a volcano away from its magma source. For millions of years, lava welled up from a fixed hotspot, spilling out in broad, overlapping flows. Each eruption added another thin layer, spreading outward instead of piling up. Over time, these flows built a mountain so wide that it reshaped the local gravity field, bulging the planet's surface and even warping the Martian datum, the very baseline scientists use to measure elevation. Mission after mission has scanned Olympus Mons, from Mariner 9's first blurry images to the high-resolution data of Mars Global Surveyor and Mars Reconnaissance Orbiter. Laser altimeters traced every contour, mapping the gentle rise of the shield and the abrupt cliffs that mark its outer edge. The volcano's caldera spans 80 kilometers, a collapsed roof where the mountain's weight finally overcame the support of the underlying rock. Around the base, steep escarpments drop as much as 6 kilometers to the surrounding plains, marking the boundaries of ancient landslides and lava deltas. Olympus Mons is more than a record holder. It is a monument to a planet where the rules of mountain building are rewritten. The low gravity and lack of tectonic drift turned a single volcanic hotspot into a construction site for the largest shield in the solar system. Its slopes, mapped in detail by orbiters, show a world where scale is measured not just in height, but in the sweep of the horizon and the vastness of the base. On Mars, a mountain can rise so slowly and so wide that the summit becomes a continent, and the climb is measured in days, not steps. Vesta is a world where mountains are born in the blink of an eye. At just over 500 kilometers across, this battered asteroid looks unassuming from afar. But swing past its south pole, and the surface plunges into a vast crater called Rhea Silvia. At its center stands a spike of rock that reaches 22.5 kilometers from the deepest floor to the highest tip, a climb that by base-to-peak standards tops every other mountain in the solar system. Unlike Olympus Mons, which took millions of years to build up layer by layer, Rhea Silvia's central peak was created in an instant. About 1 billion years ago, a massive object slammed into Vesta at cosmic speed. The impact nearly shattered the asteroid, carving out a basin 500 kilometers wide, almost as large as Vesta itself. The force was so intense that the ground behaved less like solid rock and more like a thick liquid. As the shock wave punched into the core, the crust rebounded, splashing upward at the center of the crater. In that moment, a mountain taller than Everest, Mauna Kea, or even Olympus Mons, at least by some measures, was born. Planetary scientists call this process impact rebound. It is the same phenomenon you see when a droplet hits a pool of water. The surface caves in, then a spike of liquid leaps up from the center. On Earth, gravity and erosion would quickly flatten such a spike. But on Vesta, gravity is so weak, less than 4% of Earth's gravity, that the rock does not slump. Instead, the mountain freezes in place, a permanent monument to the violence of its birth. The strength of the rock itself, not the pull of gravity, sets the limit for how tall a mountain can stand here. NASA's Dawn spacecraft arrived at Vesta in 2011 and mapped every contour of Rhea Silvia's basin in detail. Its digital terrain models confirmed that the central peak rises more than 22 kilometers from the crater floor, give or take a few hundred meters, depending on how you define the base. Dawn scientists debated the numbers, but the conclusion was clear. Vesta's spike is a record breaker if you measure from the deepest pit to the highest point. As Dawn's principal investigator Chris Russell put it, Vesta steals the crown if you measure fair. What makes this possible is not just low gravity. On a world this small, rock is incredibly strong compared to the feeble force pulling it down. Theoretically, you could build a mountain on Vesta that rises 50 kilometers or more before the rock would finally collapse under its own weight. In practice, nothing in the solar system has managed it yet. But the physics are clear. Here the rules that limit mountains on Earth and Mars simply do not apply. Dawn's stereo maps let scientists trace the splash pattern of the impact, revealing not just the central peak, but a ring of secondary mountains, all frozen mid-motion. The basin's walls are scalloped and fractured, evidence of the shock that nearly tore Vesta apart. Yet the asteroid survived, and its central spike still towers over the landscape, untouched by erosion, wind, or rain. On Vesta, a mountain can be born in seconds and last for billions of years. The story of Rhea Silvia's central peak is a reminder that not all mountains are built by slow, steady forces. Sometimes the tallest summits are formed in a single catastrophic moment, when the ground itself splashes like water and gravity is too weak to pull it back down. For planetary geologists, Vesta is a natural laboratory, a place where the physics of impacts and the strength of rock play out on a grand scale. And for anyone measuring mountains, it is a world that rewrites the record books, one impact at a time. Io orbits deep within Jupiter's gravity well, where tidal forces stretch and squeeze its interior like a ball of putty. This relentless kneading drives hundreds of active volcanoes, but the moon's tallest mountain is not volcanic. Busaule Montes rises about 17.5 kilometers above Io's tortured plains. That summit is higher than any peak on Earth or Venus, and nearly as tall as the Great Shield Olympus Mons. Yet Busaule's origin story is a geological curveball. The Galileo spacecraft's images revealed a landscape scarred by immense blocks of crust, some standing upright like the broken teeth of a colossal gear. Unlike volcanoes which build up gently over time, Busaule Montes is a thrust block, a massive slab of ancient crust wrenched upward by tectonic forces. On Io, the surface is constantly resurfaced by lava, burying older layers faster than on any other world. The crust cannot keep up. As new volcanic plains pile on, the older surface is forced to crack and break. When the tension snaps, huge blocks of rock are thrust up at steep angles, exposing fresh faces and creating cliffs that drop for kilometers. The process is powered by tidal heating. As Io races around Jupiter, the planet's gravity flexes the moon's interior, generating enough frictional heat to melt rock and drive eruptions. But this same energy also tears at the crust, building up stress until the surface fails. The result is not a neat mountain range, but a jumble of tilted slabs, some nearly vertical. Busole Montes is the largest of these, a monument to a world where the ground is always on the move. For the Galileo science team, the discovery was a surprise. They expected volcanoes, but instead found tectonic peaks, proof that on Io, the tallest mountains are built not by eruptions, but by the relentless pressure of a world pulled between gravity and fire. Busole's summit stands as a testament to the strange geology of the Jovian system, where even the tallest peaks are shaped by forces no mountain on Earth could survive. Iapetus doesn't just have a mountain, it wears a wall, stretching nearly 20 kilometers high and running for over 1,200 kilometers along the moon's equator. The ridge on Iapetus is one of the most baffling structures in the solar system. Cassini's flybys in the 2000s revealed its full scale, a sharp-edged barrier as tall as the Himalayas, perfectly tracing the equator. But the real puzzle is not just its size, it is how this wall came to be. The debate has kept planetary scientists busy for decades. One idea points to Iapetus's ancient past, when the moon may have spun much faster than it does today. If Iapetus once rotated every 16 hours instead of its current 79-day period, centrifugal force could have flattened its shape, puffing out the equator and forming a bulge. As the moon slowed and cooled, that bulge might have frozen in place, leaving a fossilized ridge. But Cassini's topographic maps throw a wrench into this theory. The ridge is far too narrow and steep compared to what a spinning body would produce. It is also patchy, not a continuous belt, and sits atop the bulge rather than blending smoothly into it. The numbers just do not quite add up. Another camp argues for a more dramatic origin, a ring system like Saturn's that collapsed and rained debris onto the equator. In this scenario, a collision or a captured object left Iapetus with a temporary ring. Over time, the debris spiraled down, piling up a mountain range exactly where the ring's shadow had circled the moon. The evidence is tempting. The ridge's sharpness, its equatorial location, and the gaps where later impacts have erased sections all fit with the idea of infalling material. Crater counts show the ridge is younger than the surrounding terrain, supporting a late catastrophic event rather than a relic from the moon's birth. Cassini's data has not settled the argument. Crater statistics, ridge morphology, and the lack of flexure at the base all lean toward the ring hypothesis, but no direct traces of ring material remain. Meanwhile, the rapid spin model can explain Iapetus's overall shape, but not the ridge's precise form. For now, the equatorial wall stands as a mystery, a structure that defies simple explanation, inviting new missions and fresh ideas. On Iapetus, the tallest mountain is not just a record breaker, it is an unsolved case written in ice and rock. Miranda, the smallest of Uranus's major moons, holds a record that feels almost like a dare to the laws of physics. Here, etched into a battered world only 470 kilometers wide, stands the tallest known cliff in the solar system, Verona Rupes. For decades, planetary scientists and Voyager 2 engineers have argued over its true height. Early estimates, based on the grainy images Voyager snapped in 1986, soared as high as 20 kilometers. Later, when the stereo pairs were reanalyzed and the distortions corrected, the numbers settled closer to 7 to 10 kilometers, a drop that still dwarfs anything on Earth. Miranda's gravity is only about 0.008 times Earth's. That means if you stepped off the edge of Verona Rupes, you would fall for over 7 minutes before hitting the base. The math is simple, but mind-bending. From a height of 7 kilometers, with gravity at 0.07 meters per second squared, the free fall stretches out to nearly 450 seconds. On Earth, a skydiver plummets from a plane and lands in under 2 minutes. On Miranda, the same leap becomes a slow-motion descent with plenty of time to ponder your choices. The impact at the bottom, though, would be less dramatic than you might expect. With so little gravity, even after 7 minutes, you would hit the ground at around 40 meters per second, roughly 90 miles per hour. That is fast, but not fatal if you had a decent airbag. In theory, a careful jumper could survive the tallest cliff in the solar system with only a bruised ego. Verona Rupes is not just a curiosity for thrill seekers. The cliff marks the boundary between Miranda's ancient cratered highlands and its younger grooved terrain, a scar left by the moon's chaotic past. Some planetary geologists think Miranda was nearly torn apart by tidal forces from Uranus, then reassembled by gravity, leaving behind giant faults and cliffs. The surface is a patchwork of water ice, frozen as hard as granite at these frigid temperatures. For Voyager's engineers, mapping Verona Rupes meant pushing the limits of 1980s technology, piecing together a world where the rules of mountain building and falling are written by gravity's weakest hand. Pluto's mountains are made of something earthly climbers would never expect: water ice, frozen so hard by the cold that it acts like stone. The Tenzing Montes, named in honor of Tenzing Norgay, rise up to 6.2 kilometers above Pluto's plains. At these temperatures, nearly minus 230 degrees Celsius, water ice becomes as strong as granite. It can hold sharp ridges and steep faces for millions of years, resisting the slow creep that would flatten a mountain anywhere else. When NASA's New Horizons spacecraft swept past Pluto in July 2015, the geology team was stunned by what they found. Tenzing Montes and its neighbors tower over a landscape that, at first glance, looks like a frozen Alps. But beneath their icy peaks, the ground is not solid rock. These mountains float atop a vast, slow-moving glacier of nitrogen ice. Nitrogen, soft and pliable at Pluto's frigid temperatures, forms a kind of frozen sea. The water ice mountains are like icebergs, anchored but buoyed up by the denser, more rigid material below. The New Horizons, scientists debated the makeup of these peaks in the days after the first images arrived. Spectroscopy confirmed the summits were water ice, not methane or ammonia. The hardness of water ice at these temperatures gives it the strength to rise kilometers above the plane without slumping, a property that would be impossible closer to the sun. It is a twist on mountain building. Instead of rock on rock or ice on rock, Pluto's mountains are ice on ice, hard water ice floating on softer nitrogen. This cryogenic geology flips our expectations. On Pluto, the building blocks of mountains are the same as the building blocks of snowmen on Earth. But out here, water ice is the bedrock, and nitrogen is the glacier. The peaks of Tenzing Montes remind us that, in the deep freeze of the Kuiper Belt, the rules of mountain building are written by temperature as much as gravity. New Horizons gave us the first close-up of these frozen giants, a world where even the tallest mountains are icebergs locked in place, harder than stone, and shining under a distant sun. Right now, the tallest mountains in the solar system exist not on thriving worlds, but on silent frozen bodies where gravity yields to geology. As we prepare to send new missions, robotic and human, to these distant places, each summit holds clues about planetary evolution and our own limits. The boundaries of what is possible are not set by Earth alone. Somewhere out there, the next definition of impossible is waiting. Share your thoughts below.